Okie dokie, guys. So let me very quickly recap some of the things that we said yesterday. So to begin with, the broad subject that we're talking about are positivity constraints on the signs of higher dimension operators. In any effective field theory, including the effective field theory of our real world, by the end of the day, I'll show you just a plot what some of these predictions on for photon-photon scattering, photon-graviton scattering, et cetera, look like, you know, the theory of the actual world out there. I reminded you of some of the very simple earliest examples of such constraints on things like the signs of d phi to the 4 terms or f to the 4th ff dual square terms in theories with a U1 gauge field. And I didn't mention it yesterday, I'll just mention it very quickly now, that these constraints have some interesting implications. They're a little surprising from the completely standard Wilsonian picture of effective field theory. Of course, it's not in contradiction with it at all, but it's surprising that you can say something about high energy physics without going there, even something without going to higher energies directly, even something as mild as these signs. And they're related to some of the other, so even though these are non-gravitational statements, the ones that I made yesterday are not manifestly gravitational statements, they're related to some of the gravitational statements that we heard Hiroshi summarizing in the last lecture. For example, it was already pointed out back in those early days that if you imagine you taking an extremal black hole, and higher dimension operators have the effect of changing the mass to charge ratio for extremal black holes, as Hiroshi was reviewing. Well, you can ask the question, what happens if you take the f to the 4th operators, or ff dual squared operators, say those guys, and what do they do to the mass to charge ratio? And it turns out that precisely when they have the correct sign, in order not to screw up the superluminality, unitarity, causality arguments, are when they push the mass to charge ratio of extremal black holes down in order to be compatible with what you would think from the weak gravity conjecture. And this is not so surprising that there should be a correlation between protecting unitarity and causality on the one hand and consistency of black hole thermodynamics on the other hand. The way I like to think about it is that gravity is sort of consistently coupling to theories that respect causality and unitarity, and it would be kind of a disaster if you're screwing up with the notion of the existence of a light cone, if you're, which is what goes wrong when you're allowed to go faster than the speed of light, then you're screwing up with the universal notion of a horizon. And if you screw up with the universal notion of a horizon when you have gravity, you're completely screwed when it comes to assigning universal meaning to things like the area of the horizon. Well, if you don't have a notion if the notion of the light cone is messed up by your ultraviolet physics, then it's not surprising that you're going to mess up things that have to do with the black holes. So another application of these things, there are various interesting effective field theories that that were originally people ran into in the context of theories of massive gravity. If you look at theories of massive gravity, and there's various types of them, but the sort of best, most healthy seeming theories of massive gravity, just like you can do with theories of massive spin 1 particles, sort of take a decoupling limit and just study the dynamics of the longitudinal modes of these degrees of freedom. So if you do that for massive non-abelian gauge fields, you recover the dynamics of the Goldstone bosons being that of the nonlinear sigma model. And so that's perfectly fine. That's a healthy effective field theory. It breaks down in the ultraviolet and needs a UV completion. But by itself, it's a perfectly healthy effective field theory. If you do that for the best possible theories of massive gravity, you find that in that case, the extra longitudinal degrees of freedom must enjoy an interesting, in that case, the scalar longitudinal degree of freedom, just that one guy. So you just have a theory of a single scalar field, but it has to enjoy an interesting shift symmetry. Not just a symmetry under shifting phi goes to phi plus constant, but a symmetry under shifting the derivatives. D phi goes to d phi, d mu phi goes to d mu phi plus c mu. That's why we called this the Galilean symmetry a long time ago when we ran into this symmetry in that same superluminality paper. And that symmetry, in turn, forces the coefficient of the d phi to the 4 term to vanish. Okay, so it's directly a consequence of that symmetry that if you try to write down an effective Lagrangian, it's clear d phi to the 4 is not invariant under shifting d phi. And so that symmetry precisely forces the coefficient to vanish. The leading low energy amplitudes actually go like s cubed plus t cubed plus u cubed rather than s squared plus t squared plus u squared. The leading one actually vanishes in the forward limit at order s squared, and therefore is in complete contradiction with the bounds that we're talking about. Okay, so that's a quick explanation. Many people had tried to embed the theories that gave you that kind of dynamics in string theory and other reasonable ultraviolet theories, and people failed over and over again. And again, this is a sort of a simple reason why it had to be the case. So already those very old positivity statements have some interesting connections to other features of, they tell you something about effective field theories that are not completely obvious ahead of time, and they do, they're related to the weak gravity conjecture, and they do appear to rule out otherwise completely healthy seeming interesting effective field theories that are even governed by some very interesting symmetries. Or at least rule them out in the sense of being incompatible with these standard principles of causality and unitarity in the ultraviolet. Again, despite the fact that everything seems hunky-dory from the perspective of low energy effective theory. So the way I like to summarize already that old story, and then what we're seeing much, much more of now, and you'll be seeing more of in the rest of these lectures, is that the world is not like a crappy metal. Okay? That there's much, much, much more constraint from the structure of Lorentz invariant unitary causal theories. They come down in the ultraviolet and they shape the possible low energy effective theory much more than you would have naively expected. And of course, as what I'm going to be telling you about today are an infinite number of things about all of these higher dimension operators. I summarized yesterday. We'll be talking about nonlinear constraints on them, linear constraints on them, a whole bunch of new constraints on these coefficients. Unfortunately, there are constraints on all these teeny tiny effects that nobody cares about. Okay, so I'm telling you an infinite amount of things on things that nobody cares about, okay, at 0th order. So the amount of progress in this subject is 0 times infinity, okay? And so depending on what you think of 0 and infinity, you can get any limit that you want for that answer, okay? But my hope is that we're just starting to see that, and you know, it's, you'll see we get very tight little regions in which a lot of these, in which effective field theories can live. Lots of seemingly very different theories end up on top very close to each other in the allowed possible space simply because there isn't that much room for them. And I hope this is the beginning of understanding more. I mean, ultimately, you don't want, if you have a fantasy about the physics of the ultraviolet telling you something new about the hierarchy of the cosmological constant problem, you want not just the ultraviolet to come down and tell you something about the higher dimension operators, but to tell you something about the marginal and the relevant operators too. We're not anywhere near that at the moment, but anyway, it is a step in that direction. All right, so that's a philosophical summary. Let me now remind you what we're actually trying to do. And I already showed that this representation for a 2-to-2 scattering amplitude is valid, and we sort of derived it when you imagine that you're that you're talking about a situation which is, in conventional language, at tree level. Okay, so you're either integrating out in a field theory a bunch of particles at tree level, or even in string theory, you're talking about string theory at tree level. What that means invariantly is a statement about the amplitude is that in an approximation of the amplitude only have poles, and we found this representation where, after taking out some subtraction terms, the amplitude could be written as a sum with some over a spectrum. The sum could be an integral, and over some spins of some positive coefficients and these Gegenbauer polynomials. And we had a propagator in the S channel and also one in the U channel. And I remind you, we're talking about the 2 to 2 amplitude for scattering that looks like particles AB goes to AB. If A and B were the same, then we'd expect the answer to have a symmetry in S, T, and U, right? Fully both symmetric. Since we're imagining a little more generally it's AB to AB, we only have a symmetry in S and U, interchanging S and U, but not in T. And so that's why I have the same residue in the S and the U channels. And I should also say that here, for simplicity of just a presentation, I'm assuming that the A and B are scalars, but there's an extension of this if A and B are any massless particles with any spin, in fact, any massive particles, but for simplicity, massless particles of any helicity. You can find the details of what the analog of these Gegenbauer polynomials are, the sort of spinning analog of the Gegenbauer polynomials, at least in 4 dimensions, are written down very explicitly in a paper I wrote last year with Yutin Huang on scattering amplitudes for general masses and spins. Okay. Now, in a moment, where all the action is going to happen is we're going to come back to this formula and just expand in S and T, and then figure out what again, the positivity of these coefficients and of the fact that the mass squareds are positive. Those two positivities are going to tell us something about the structure of the expansion in S and T. But the first thing I want to do is justify that this expansion is also true in complete generality, okay? Not just when you imagine the amplitudes only have poles, but in the most general situation where they have branch cuts as well, okay? And again, intuitively this is not unreasonable because it's a lot like what you're familiar with the 2-point function and the Challen-Lehmann representation that looks like the general 2-point function looks like the sum over a bunch of tree propagators. We want to see the analog of that for amplitudes. Okay, and so really all this means is that we want to show that and once again, I remind you that I'm working in an approximation where I've integrated out massive particles. I'm ignoring the low energy loops. So I'm ignoring what you could call the running of these higher dimension operators as we go to low energies. I'll say a little bit about the running at the very end today and its connection at least in a couple of situations, because there's some interesting positivity statements about those beta function coefficients that's related to supersymmetry and the weak gravity conjecture. Actually, an asymptotic proof, a proof of an asymptotic version of the weak gravity conjecture that I'll mention at the very end of the talk. But what it means that we're ignoring those low energy cuts then is that if I imagine I'm working again at T fixed negative, that in the S plane, I want to understand what's the analytic structure of the amplitudes. And there's one thing that we expect. We expect that there's a branch cut somewhere where the massive particles start, both in the S channel and in the U channel, out here somewhere. And again, these are the normal thresholds that we expect. These had better be there. They occur for real Lorentzian momenta. The discontinuity, the imaginary parts you see, no one is disputing without saying anything about the complex plane that for real Lorentzian momenta, the amplitude has an imaginary part given by unitarity, right? The S matrix for real Lorentzian momenta is unitary, S dagger S equals 1, and so all the consequences that follow there are true without saying anything about the complex plane, all right? So there's somewhere here, there's a discontinuity associated with the normal thresholds, and they're correctly given, and the discontinuities are correctly given by unitarity. So all we have to now show is that those are the only ones that are there, and nothing else. So what else could we have? We could have some crappy thing here on the real axis. Who knows? We could have something off in the imaginary plane somewhere, right? What if the amplitude had branch point singularities of some sort elsewhere in the S plane? That's what we're trying to control, because if those exist, they are not directly controlled by unitarity, And so then a different game begins, okay? And as we'll see, they are out there in general, okay? And so that's why, like, flat-out Lorentzian unitarity is not enough to play the S-matrix game, and people talked about generalized unitarity and lots of other things, and the whole program ran out of steam because it started looking more difficult. So this looks very intuitive that these are the only singularities, but in fact, it's false in general that they're the only singularities, and it's possible to have singularities elsewhere. I want to just review what we know about the singularity structure of scattering amplitudes to be able to confidently say that there is some regime where it does look like this, okay? And so there is a regime that looks like this, as we'll see. For example, if I take t small, as long as t is small compared to what all these masses are. In fact, if just as t is negative, never mind small, any t negative, so it's compatible with Lorentzian kinematics when s is positive, okay? Any t negative is going to be okay, right? But if t is positive and big enough, becomes comparable to the mass of the internal particles, then it's not true. There are other singularities here that are not associated with normal thresholds, and so you have to make a different argument. Okay, so what I want to do now is just quickly review what we know about the analytic structure of general scattering amplitudes, but then 2-to-2 scattering amplitudes particularly. Any questions so far? All right, now we're interested in looking at the analytic structure of, loop diagrams. Imagine some arbitrarily complicated loop diagram. And we have very poor methods for understanding the analytic structure of these amplitudes as a function of the external data. In fact, essentially the only method that we have, and it's very coarse, unbelievably coarse, are what I'll now review as the Landau equations. How many people have heard of Landau equations, other than the people who've worked on Landau equations? All right, excellent. Landau will be rolling in his grave. Okay. The first thing that we're going to do is so we can't carry out this actual loop integral. Oh, by the way, just so I'll slide this up and down. Oops. For those of you who've never looked at these things in your life, this is the kind of thing that we're actually after, okay? So something as trivial as a one-loop box diagram, okay, in 4 dimensions. This is what the answer is, right? And you see the answer is chock full of log squareds and dilogarithms. Okay? And the arguments involve some interesting square roots. And I'm just flashing it for the moment here just so you see, the actual answers are not trivial. They involve these transcendental functions, logs and dilogs. And that, of course, shouldn't surprise you. These transcendental functions, logs and dilogs, have branch cuts. And there are discontinuities across those branch cuts are supposed to be there because of unitarity. But that's what we'll come back to in a second. Some of these things have to be there because of unitarity. Other ones are not obviously related to standard unitarity. They're related to generalized unitarity. Okay. We'll come back to this in a little bit. But that's just supposed to tell you that you're not, we have no hope of analytically doing these integrals in complete generality and saying anything about them. Okay, we have to say something a little more on general grounds. So the first thing that we're going to do is Feynman parameterize. So let me remind you that Feynman parameterization is that 1 over d1 through dn. You imagine writing each one of these in terms of Schwinger parameters. I'm going to ignore the i's from 0 to infinity, but the important point is the integrals over the Schwinger parameters from 0 to infinity. And then if you take out the overall scale of all the Schwinger parameters, you can do that integral, and you're left with n-1 integrals. The normal way of writing this in the physics literature I hate. I absolutely loathe these things with delta of 1 minus the sum over alphas. So if you take nothing else from this lecture, it said never write it that way again. Because anyway, there's nothing incorrect about it, but that delta just really bothers me. So this is an integral over alpha is positive because it's obscuring something. This is really a projective integral. It's an integral over a Pn minus 1 projective space. The whole point is that we're taking all the alpha variables up to overall rescaling. The measure on the projective space, now we have n minus 1 alphas, so it's again alpha contracted with n minus 1 d alphas, and it's over alpha 1 d1 plus dot dot plus alpha n dn to the n. So this is an integral over a simplex in Pn minus 1, the simplex just being where all the alphas are positive. Okay? And now you're free to choose any coordinates you like on the projective space, and then you would get any one of the usual answers. The one where you say that the sum of all the alphas is 1 is just one of an infinite number of different ways of putting coordinates on the projective space, and there's no particular reason to privilege it over any of the others. Okay, so that's really what it is. And so what we end up getting then when we Feynman parameterize something is we end up getting an integral. Let's say we're in 4 dimensions, it doesn't matter. An integral in d dimensions over the internal loop variables. Maybe some numerator that we're not going to care about so much. We care about the structure of the denominators here. But downstairs we're going to get something that's the sum over all the edges of the Feynman graph, alpha e times the momentum in that edge times the propagator. So it's a momentum of the edge minus the mass squared of the edge. And then it's going to be to some giant power for the total number of the total number of internal lines. Okay? Capital I, let's say the total number of internal lines. Okay, so we have that, and of course the integral, this integral over the Feynman parameters. So it would be alpha di alpha, di minus 1 alpha. So all the alpha edges positive. Okay. So now comes the, and of course there's an I epsilon here in the propagators. And just to make the trivial point, the entire purpose of the I epsilon is so that it guarantees that this integral actually makes sense when you compute for real momenta. The integral is convergent, makes sense, we know what it is. Okay? So there's no ambiguity in what the integral is. Note that it's slightly important that the alphas are all positive, so that when I sum over all these weights, the coefficient of the I epsilon is positive everywhere. It never goes to 0. When I say finite, of course, it could have ultraviolet divergence and so on, but that's not what I'm talking about. I'm talking about just the hitting the poles. Imagine we've regulated this somehow. Okay. So now comes the question. So these L's depend on the K's and they depend on the external momenta in the usual way. You know, we draw the loop, the momenta flowing through the graph. So the L's depend on the loop momenta and on the external kinematics. And now we'd like to ask, as we move the external kinematics around, we're interested in the structure of this for general external kinematics. Where can the answer have singularities? Okay, now obviously the answer can have singularities when the denominator goes to 0. But you need more. And I'm going to be a little impressionistic here, just for the sake of time, but you can fill in the blanks yourself. It's a very simple argument. You need more. Like, it isn't enough, if you imagine here's a contour of integration, it isn't enough as you're moving things around to have one singularity approach the contour of integration. Because if that happens, you can just move the contour a little bit. You know, if it comes here, you can just move the contour down and avoid the singularity. When you're in trouble is when you get a pinch. So when you have so this is a place where the integrand diverges. This is another place where the integrand diverges. And what's bad is if you move the external kinematics around and these things pinch. Okay? Then you have a singularity that you cannot avoid. And so it's not enough to have this denominator d So d is a function of the alphas and the k's. It's not enough for d to go to 0. So to have a singularity, we have to have d goes to 0. But also, we have to have that it's a critical point. Okay. So in other words, we have to have multiple. We have to have at least two singularities colliding. So that means that d has to be actually at a stationary point. So not just that d goes to 0, but the derivative of d with respect to both the k's and the alphas is equal to 0. There's another possibility, which is that the integral that we're talking about, especially the integral over alphas, has a boundary at alpha equals 0. So another possibility is if the singularity is reached when alpha goes to 0. Right? That's also okay, but alpha going to 0 just means that we erase that propagator from the diagram. Okay? So if you want to know about the possible singularities of a given diagram, what you have to do is take the diagram and also all the diagrams that you get from it by shrinking propagators. Okay? So you have to allow that possibility. If we do that, we don't have to worry about this second case. We're just taking into account where the alpha can go to 0. Yes?
What about infinity?
When alpha goes to infinity, it's like I think you need to separately worry about what happens when alpha goes to infinity. Yeah. Yes, in this case, you separately have to worry about it. But at least we're not, the case where alpha goes to a 0 is taken into account. All right. So what are the equations that we're talking about then? So these equations tell us two simple things. These are the Landau equations. They tell us that I think, Sasha, the good answer to your question is that alpha goes to infinity is not a meaningful place projectively. Okay? So the actual singularities, yes, that's right. So the real singularities are on the boundaries of this simplex. And that in some coordinate, in one of the coordinate patches is just where any one of the alphas goes to 0. So if you do some other fixing, then it could be that some of them are going to infinity, but that's secretly another one goes to 0. So in fact, they're all the alphas going to a 0. They're just the boundaries of this simplex. There's nothing extra at infinity. All right. So what are these Landau equations? First, the derivative with respect to the alphas just tell you that all the internal lines are on shell. So for every edge, LE squared minus ME squared equals 0. And 2, for every loop, for every closed loop, the sum of alpha E LE mu is equal to 0. Right? That's what you get by differentiating with respect to the K of that loop. And in general, if you routed the momenta randomly, you might have plus or minus signs in this formula. Here I'm imagining I've routed all the momenta and all the diagrams so the loop momenta have a standard orientation so that the sum of all the loop momenta, well, anyway, I won't say more about that. Okay, so now the question is, can we find solutions to these equations? Right? If we can find solutions to these equations for some external kinematics, then at the place where we find those solutions, the amplitude can have a branch singularity of some kind. And in complete generality, these are multi-valued functions. You already saw they're logs and dilogues. If you want to think about where the singularities can be anywhere on any sheet of this analytically continued object, they should have some correspondence with the solutions of these equations. But if we're interested in one other thing, we're interested in the amplitudes on the physical sheet, like the actual, the first sheet on which they're defined. Well, we need one more condition. So on the can you guys see this? Let me bring this up a little. On the physical sheet, you want to encounter the singularity on the contour of, on the actual contour of integration, so you want to have that the alphas are positive. Okay, now, on the face of it, I just want you to look at this for a second, because we're going to get, in general, unoptimistic and then optimistic, okay? Because if you look at these equations don't look so bad, right? There's a bunch of, and actually before I say any more, so there are some quadratic equations here that says L squared equals M squared, and then there are these also quadratic in alpha and L equations, okay? So the Landau equations are a bunch of coupled quadratic equations. And they depend on parameters, okay? So solving a bunch of coupled quadratic equations is not easy. Solving a bunch of coupled linear equations is easy. Solving a bunch of coupled linear equations is easy because geometrically each linear equation's vanishing locus is associated with the hyperplane, and there's the trivial geometric fact that two hyperplanes intersect in a lower hyperplane. So planes intersect into planes. These are quadrics. These are quadratic equations. And it is not true that quadrics intersect into quadrics or anything else. And for that matter, it's possible to prove that an arbitrarily complicated, any algebraic variety can be realized by intersecting quadrics. Already something as simple as quadrics. Okay? So a priori, it's not at all obvious. So a priori, you stare at these equations and think they have complex solutions up the wazoo everywhere. And it's very hard to say anything about them. In particular, just abstractly ahead of time, it's not remotely obvious that the solutions to these equations should pick out of all possible things Lorentzian external kinematics and have those branch points correspond to normal unitarity thresholds, just without doing anything. That would seem to require some miracle for something like that to be true. Is that clear? Right? These are complicated nonlinear equations. They should have complicated complex solutions in general. There's no reason to think that they pull out of the ether just things that matter in Lorentzian signature. And indeed, they don't in general. All right? Oh, let me make one other comment. Actually, this is a nice exercise for you. You also want to convince yourself that when this happens, you're actually pinching. It isn't just that the two poles are coming together from one side of the contour, but they're actually pinching. And that's actually very, very simple. You just go to the neighborhood of where this denominator vanishes. You make a quadratic approximation to D, and because of the I epsilon that's sitting there, you can see that the poles are actually approaching the contour from the opposite sides. But anyway, yes? Well, we don't, I mean, this is where some singularity is, okay? Yeah, so there's some, yeah, this is where we can encounter some singularity, some non-analyticity of the answer at these places. Sorry? Well, we don't expect to get poles in loop integrations like this. That's right. At tree level, we can have poles. Now we're talking about, so if you have exactly stable particles, we can have poles. Now all of these things are going to be branch points. Now, let me give you some examples of how this works. Boy, I'm going pretty slow. So let's see something very simple, like let's begin with a familiar two-point function. Okay, so not even an amplitude yet. Okay, and now, for simplicity, I'm going to imagine the internal masses are just m. So what are the Landau equations? They're L squared equals m squared. From that one, L plus p squared equals m squared. And also that alpha 1, L1, plus alpha 2, L plus p equals 0. Sorry, L. Okay, so these are the Landau equations. So from here, we can discover that, well, 2L dot P equals negative P squared. And so let me take this vector equation and let me get two scalar equations out of it by dotting with L and by dotting with L plus P. Okay, so if I dot this equation with L, I get alpha 1 m squared. And then from here, when I dot with L, I get alpha 2, that's m squared. But from here, I get p dot L, which is negative 1/2 p squared. Okay, so I get this equation. And then if I dot this equation with L plus p, I get the other equation, just obviously symmetrically on the other side. Okay, so these are the equations that we're dealing with now. We put them on shell, so now I have 2 equations and 2 unknowns for the alphas. And so now you see what the challenge is. I'm sorry, thank you. So let's write this as a little matrix equation. So I have m squared minus 1/2 p squared, m squared minus 1/2 p squared, m squared, alpha 1, alpha 2 equals 0. And therefore, the generic solution is alpha 1, alpha 2 equals 0. Okay? And that's not the one we want. We want solutions here where the alphas are positive, both positive. Okay? So first, what does it take to have a solution where the alphas are not 0, where the determinant of this matrix had better vanish? So we learn that, so det of this guy is equal to 1/2 p squared times p squared minus 4m squared has to equal 0. Okay, so we discover that there is potentially a branch point either when p squared equals 0 or p squared equals 4m squared. Now, when p squared equals 0, let's go back and see what the solution is, right? When p squared equals 0, this matrix is m squared, m squared, m squared, m squared, and so what is the 0 eigenvalue? It's 1, negative 1. And so that's not the solution we want. That's not on the physical sheet. Can't be on the physical sheet because one of the alphas is positive and one of them is negative. But the other solution, when p squared equals 4m squared, in that solution, this is m squared, negative m squared, and that's a solution where both the alphas are positive. Okay? So we see that the Landau equations put a constraint on the external kinematical data, and the one which has the alphas positive is indeed the one that we know should be there. It's the physical threshold when p squared equals 4m squared. All right? Okay, so now already let me stick here and imagine going to much more complicated loops, but still with the 2-point function. And before doing that, I should mention, just for intuition, it's just names for these linear equations, that these linear equations have a nice interpretation. Okay, so if you take your graph, and I just imagine, routing momenta through it somehow, then the L's, the LE mu, forgetting about the mu index, can be thought of as a current. So if an edge joining V to V prime as a current from vertex V to V prime, and the alpha parameter can be thought of as a resistance. So you can think of it as an electrical resistor network. And therefore, this equation is just Kirchhoff's law, okay, that says that the voltage drop going around a closed loop is 0. And of course, momentum conservation at the vertices is current conservation. Okay? So these linear equations, the linear part of the Landau equations are exactly the same as an electrical network problem. I'm mentioning that just so you have some intuition for what we're now about to say, for why it is that in complete generality we can say that the only thresholds associated with the 2-point function, I mean now I'm just trying to say Challen-Layman again, but in a more mechanical way, looking at possible loop diagrams. The point is, whatever the heck you have there, you can solve the linear part of the Landau equations. The internal loop momenta you can express in terms of the ones on the outside and the external data. And the act of doing that in the language of electrical networks is to take some part of the network, shrink it to a point, and you know that the entire effect of that is absorbable into redefining what you meant by the resistances of the rest of the network, right? And therefore, of course, and the Landau equations are not just electrical, because those are just the linear equations. We also have the on-shell conditions, okay? So they're more complicated, but we don't lose information. You gain more constraints, but you certainly don't lose any. So you're free to imagine reducing, reducing, reducing down till you get to this bubble, okay? And then you see that all the thresholds are normal thresholds associated with the particles that could be produced. Okay. Now let's move on to a slightly more interesting example of the box diagram. Now I'm going to, just for simplicity again, imagine that all the external particles are massless. But I have some internal mass m, little m. Doesn't matter. All right. Now I have some L plus P1, L plus P1 plus P2, L minus P4. Once again, I have all the on-shell equations. So all the Li squared here are equal to m squared. And then it's a trivial exercise that I won't do for you now, just the exercise in kinematics, to see what the various dot products are. Okay, so for example, if I take two dot products of an L and an L prime that meet at a corner, that dot product, L dot L prime, is equal to m squared. Whereas two L's and L primes that are far apart from each other, like this L and L prime, this L dot L prime is equal to m squared minus a half of the momentum flowing in between them, of the kinematic invariant flowing between them. Okay, so that's just the, I'm saving space by not writing down 6 equations for all pairs. And so now we can write down again, I have the Landau equation of alpha 1 L1 plus alpha 4 L4 equals 0. But if I dot this equation into each one of the 4 loop momenta, I get 4 equations. And those 4 equations are the following. 1 minus a half s over m squared, 1. 1 minus a half t over m squared. 1 minus s over m squared. 1. Okay. So those are the 4, those are the Landau equations you get by dotting the main one into the 4 loop momentum. Now, before doing anything else, taking the determinant, before doing anything, let's just make a qualitative comment. If any one of either S or T is negative, then it's obvious that there are no solutions here where all the alphas are positive. For example, if T is negative, every one of these terms in this row is positive, and therefore it would have to have a sum of a bunch of positive things equals 0. So that's impossible. So we see ahead of time that it is impossible to find interesting solutions to this Landau equation in Lorentzian kinematics. Remember, Lorentzian kinematics forces at least one of the kinematic variables S and T to be negative. We drew that, we can't have both of them positive. Fine, so that's already reassuring. 2, notice also, by the way, I should have said, where is going to be the usual threshold singularities we'd associate with this are not in this box diagram, but in reductions of the box diagram, right? I could, remember, when I'm studying the Landau equations, I have to take the diagram and also all contractions of the diagram. So that would include this guy and also include that guy and so on, okay? So the normal thresholds are going back to this example that we just did a moment ago with the 2-point function. Okay? We're now looking to see if there's something else associated with this guy. I'm going to skip talking about that, associated with this guy. And so that's what this analysis is about. All right. So now let's keep going and see if there is any funny singularity anywhere. And so if you take the determinant, the determinant is equal to 1/16 st times st minus 4 s plus t. Sorry, this is the unit I'm setting m squared to 1 here. And so indeed, there is a solution where I set, I solve this guy. Again, the ones where s and t goes to 0 don't have the alphas positive for the same reason as before, but there is a solution where I set this thing to 0 and where s and t are both positive. In fact, that solution exists not just when s and t are positive, but when s and t are both bigger than 4m squared. Okay? So you can find, and of course, you fix a value of t. For a fixed value of t bigger than 4m squared, the branch point begins at a fixed value of s. Also happens to be bigger than 4m squared, but where this equation is satisfied. All right, so this is an example of something that's called an anomalous threshold, right? It's a singularity off in the complex, not in Lorentzian kinematics. We can't reach in Lorentzian kinematics. If you tried to reach it in Lorentzian kinematics, you'd have to use complex momenta. Okay? You can reach it with real momenta in 2,2 signature. And so that means that there's a singularity that we cannot predict by standard unitarity. Okay? Now, in this case, we're not completely screwed because we have a picture of what the diagram actually looks like. We have a picture for what this singularity is. Oh, let me also just show you where it is in this answer. Okay? So this is a very complicated looking formula, but just for this purposes, I can illustrate very quickly what is going on. So, everywhere in this expression are these objects beta sub x. Oh, and I forgot to define what u and v are. U and v are 4m squared over s and 4m squared over t. So, because of this ubiquitous square root, if absolutely nothing else, there's a branch point associated with the square root when the argument of the square root goes to 0 with a minus sign. Sorry, here. So you see, for example, the branch point associated with beta u goes to 0 is just a normal threshold where s equals 4m squared. Beta v is a normal threshold where t goes to 4m squared. But there's this beta u plus v that makes an appearance everywhere here. And the threshold associated with the beta u plus v is at exactly this point that we just identified. Okay? So it's there. It's sitting there in the general analytic structure of the answer, but is not a normal threshold and is not associated with standard unitarity. Then there's a whole subject. If I had much longer lectures, I would tell you what little is known about generalized unitarity, even from this point of view of the old-fashioned S-matrix program of the 60s. Of course, in modern times, in perturbation theory especially, generalized unitarity has been put to spectacular use in actually computing loop integral and understanding all sorts of other things. But anyway, for these purposes, I just wanted you to see. So let me summarize. What little we know about on general grounds of the analytic structure of scattering amplitudes follows from looking at solutions of the Landau equations. I cannot emphasize how coarse and pathetic this is, okay? Because it just tells you where the branch points are. It doesn't tell you what the discontinuity is. In general, after we talk, if you really want to understand the analytic structure of the object, you'd take that dialogue. You don't just want to understand what the first discontinuity looks like. It has the discontinuities themselves have discontinuities. You want to find the entire analytic structure of the object, okay? So you want to know not just on the physical sheet, but everywhere underneath it, okay? So beyond that, we have to relax this assumption that the alphas are positive, and so we have no idea how to associate. Even on the physical sheet, we don't have, in general, an idea how to associate the singularities with unitarity in complete generality. Never mind what happens on all the sheets underneath it. Okay, so it's a coarse diagnostic for where singularities might make an appearance. Nonetheless, it's still one of the best things we have. Just on general grounds, you would expect the solutions to be complex and give you singularities all over the place. Absolutely no reason to expect the singularities are localized on the real axis in Lorentzian for Lorentzian external kinematics. And indeed, it's not in general, as we saw. Let me say again for clarity, when you do run into a discontinuity in the Lorentzian signature, that had better be given by unitarity, otherwise you've screwed something up. Okay, so that much is guaranteed to be correct. The question is whether there are other ones elsewhere, which in general there are. When you do happen to be in Lorentzian kinematics, there's a very pleasing interpretation of the Landau equations that I'll just say very quickly. This is known as the Coleman-Norton theorem.
Sorry, Nima, can I ask
Yeah.
a quick question?
Yes.
So you said that for the bubble you can reduce the network, right?
Yes.
Always to the original bubble. Is
Yeah.
the same true for the box?
That's right, yes. So you can, in general, reduce these problems down to simple ones in order to just, you might be missing constraints, but in other words, if you want to reassure yourself that there's some regime in kinematics where all you get are normal thresholds, then that's great for that. Okay, so because you say that whatever else might be going on, you can reduce until you get down to this problem, and then for this and here, all you ever get are normal thresholds. In general, of course, you can't. If you really are interested in the solutions of the Landau equations, you can't forget about the nonlinear part of the equations that you're throwing out when you just solve the linear ones. Okay? No, beyond perturbation, I'm sorry. Yeah, we can't say anything beyond perturbation theory. I mean, I can't say anything beyond perturbation theory. The books have some sections that vaguely seem like they're beyond perturbation theory, but I'm too scared of those sections of the book. So
another more concrete question. So in this example, so if you draw the S-plane at negative t and then you increase t, you see some singularity coming out of the cut?
no, not at negative t.
No, but
there's nothing at negative t. Yeah. Yes. Yes. Even
if the external particle is the lightest one?
Yes, even if it's massless here. Well, you see, you're switching from the you're switching from the beta u, which is a 1 plus u plus v, to well. Let me not say it on the fly. Let's look at it afterwards. Well, I mean, what's clear is that there's nothing for t negative. There is something anomalous for t positive. So I think something continuous has to happen in between. But let's look at it in detail. So the final thing I'll say is that if you stare at one of these pictures. You can also interpret when the alphas are positive, and the external kinematics is Lorentzian. When the external kinematics is Lorentzian and the alphas are positive, of course, all the internal loop momenta are Lorentzian because they're just given by linear combinations of the external ones. And then you can think of the quantity, I'll just say it in words. For every edge, alpha times L on that edge, you can imagine that the loop diagram picture that you drew is actually a picture in space-time. And you associate a coordinate with all the vertices. If you do that, if you look at the distance between two coordinates, x1 minus x2 of two vertices, you can associate that with the alpha times the L. And then the Kirchhoff law becomes trivially satisfied. The sum over any closed loop is equal to 0. Okay, so any solution of the Landau equations is associated with a picture, you just take the loop diagram, of particles propagating forward in time in Minkowski space. The forward in time being associated with the fact that the alphas are positive. You think of the alphas as the proper time that the particles are propagating on the mass shell, okay, classical propagation of particles on the mass shell in a space-time picture associated with that diagram. That's the Coleman-Norton theorem. Okay, it's really just an interpretation of what the Landau equations are together with the fact that alpha is positive means that you can think of the alphas as a proper time, forward in time, along associated with that trajectory. So that's also pleasing, a pleasing connection that at least for the singularities that are Lorentzian, they're associated with particle propagation. Okay? But again, the issue with anomalous thresholds is the existence of singularities that are not Lorentzian in general. All right. So that's a summary of what we know. But now let's, now we can go back to the problem we're interested in and say none of that actually occurs in the problem we're interested in where t is small. Okay, if t is small, far from where all these internal masses are, in exactly the regime we're trying to talk about, the effective field theory approximation, then none of those singularities are there. All the singularities are normal thresholds, and then the formula that I began the lecture with just follows trivially. Okay, so it's that t is fixed, and so we can write negative AST as the subtraction terms, again, writing the formula for the fifth time, is the sum over masses and spins, PMS, ds of 1 plus 2t over m squared, 1 over s minus m squared, 1 over. Okay? And that's because the only singularities are normal thresholds. The discontinuity across the cut is the positive operator given by unitarity, t dagger t. And as I explained in the last lecture, any positive operator on the unit sphere can be expanded in terms of Gegenbauer polynomials with positive coefficients. Okay? So, okay. So after 3 hours, I've accomplished what I thought I would accomplish in 1. But anyway, this is now our starting point. Okay? Any questions? How are we doing this, Amit? Are we stopping or are we not stopping?
It's a good point. We can stop here for 5 minutes.
All right. Why don't we stop for 5 minutes then? Thanks.